Okay, so let's continue our discussion on multivariable calculus, and this is lecture 2, right? This is lecture 2. Fine. Okay, now in this lecture, so our main goal is to define the notion of derivative, and which is obviously the utmost thing which we require, right, in order to talk about derivatives, right? Fine. Okay, now before moving on to a general case of defining a derivative where for a function from Rn to Rm, let us quickly go back to how we used to define derivatives over from R to R, okay, which is the simplest case. So recall, so if I am giving a function f from E to R, and let x naught be in E, right, then the derivative at x naught was defined to be, okay, I need x naught to be a limit point, because in order to define a limit at x naught, okay, but still that is something which you should already know. So what we can do is that we can define it as limit x tends to x naught, where we are taking all those values which are not equal to x naught to remove all ambiguity in order to define this quotient fx minus fx naught by x minus x naught. Fine. Clear? Okay. Now this is the our usual definition of a derivative, as you already know. Now the question is, can we immediately mimic out this definition for an arbitrary case? Okay, so can this be mimicked? Can we mimic this to a function f from Rn to Rm? Now here where the problem comes out, observe that if I have such a function, then fx minus fx naught, this belongs to Rm, right, while x minus x naught, this belongs to Rn. So this quotient is undefined. This quotient is undefined, right? Therefore this cannot be immediately mimicked, but we can sort of kind of deviate away from this definition a bit to come up with a new theory of derivatives which is quite relevant and which can be generalized to an arbitrary space, right? How can we do that? So the idea behind deviating out from this definition is to observe that how does derivatives geometrically look. Okay, so now this is something which you should already know in your high school classes, that suppose this is a function like this and I am considering a derivative at some point, let's say here. Okay, this is my x naught, and we know that this actually gives me the tangent at this point, right? This is something which we know. So what actually we are doing is that if I consider a small neighborhood around this point, so we are actually linearizing, right? We are approximating f by a linear function, because this tangent is a line, it's a linear function, linearizing f around x naught. Okay, in other words, we are approximating f around x naught, or around the region, in the region around x naught, by a linear function, right? This is what we call approximating by a linear function or linearizing in some sense. Okay, so when we say that f is differentiable at x naught, what we typically keep in mind is that f is approximately linear near x naught. Okay, so what we can think of it in this way, that f is differentiable at x naught is equivalent to say f is what we say approximately linear, f is approximately linear around x naught or near x naught, whatever. Clear? Fine. So we will come up with this definition, we will formulate it and then that will be something which we can immediately generalize. Okay. Now observe something immediately, an observation, sorry, an observation is that suppose let's say, yeah, okay, we can think of this as a problem. We can think of this as a problem. Okay, so this is a simple question. So, a question that let f be a function, let f be a function on AB, okay, that is differentiable at C, that is differentiable at C. Let Lx be the tangent line to f at C. Okay, prove that L is the prove that L is the unique linear function with the property that limit x tends to C, f of x minus Lx upon x by C is equals to 0. So what are we given? We are given that f is differentiable at C and Lx is the tangent line to f, okay, at C. Then what I need to prove is that this quotient tends to 0 as x tends to C. Fine. And the proof is quite simple. If you carefully observe, you just need to go via the definition. See, what is my Lx? So Lx is the line which is tangent to f at C, right? This is exactly Lx. So Lx is nothing but this line, right? Nothing else, right? It passes through f of C. Clearly it passes through f of C because it is a tangent at x equal to C. So it touches the curve at x equal to C, so it touches the curve at fc, right? Its slope is f prime C by the definition of derivatives geometrically. Yeah, so this part is clear, right? Fine. Okay. Yeah, this fine. But then, therefore, what is limit x tends to C? F of x minus Lx upon x minus C. So this is exactly equals to limit x tends to C, fx minus fc by x minus C. So I am just putting out the value of Lx here minus f prime of C. But then since f is differentiable at C, so this is just f prime of C, so this is just 0. Fine. And how do we come up with the uniqueness? Now to prove the uniqueness, we will actually get a converse of this theorem certainly. That is, if I have if I have a line K which satisfies this condition, then K needs to be exactly a tangent, okay, which satisfies the same properties as L, okay. So now if K is another such line, okay, then now f is differentiable at C, so f is continuous at C, right? Then by continuity, now K is a line, right? So K is obviously continuous. So by continuity of K and L, sorry, K and F, we have f of C minus K of C is equals to limit x tends to C, x minus C times f of x minus K of x upon x minus C, right? This can be surely done. Okay, but we are assuming that K is another such line, so it already has the property that this quotient tends to 0, right? So this should be 0, or in other words, f of C must be K of C, right? So the line intersects or touches f at C, right? Therefore, I can write kx as f of c plus some slope times x minus c. Fine. But then again, what is f of x? Minus k of x by x minus c. Then this is exactly equals to f of x minus f of c by x minus c minus m. And then if I tend, then limit x tends to c. So if I put this, fine, wait a minute, yeah. So if I put this here, and this is limit x tends to c f of x minus f of c by x minus c minus m. So what do I have here is, yeah, so this part is 0, so, and this is f prime c because f is differentiable at c. So this implies that m is exactly equal to f prime at c. Therefore, we have a line which touches f at c and its slope is same as the slope of L. Therefore, both the lines must be same. Thus, k must be equals to L. Fine? Fine. Yeah. So, what do we conclude from here is that, the following theorem. You can fill in the gaps. When I will be stating the theorem, you will see there is something left for the proof of this, but you can immediately fill in the gap. There is nothing complicated. That is, let E be a subset of R and f from E to R be a function, and L is something, some value in R. Okay. Let x naught in E be a limit point, or rather I do not require it to be in E, I just need it to be a limit point. So x naught be a limit point, then the following are equivalent. Number 1, f is differentiable at x naught and f prime at x naught is equals to L, and number 2, limit x tends to x naught, x comes from E minus x naught of the quotient f of x minus f of x naught plus L times x minus x naught by x minus x naught is 0. Right? Now you can immediately observe what is actually happening out here. Okay, so I am not writing out the proof because I have already written down the proof. See, if f is differentiable at x naught, then you can just take the mod of the whole limit, which will be equal to the modulus of the limit of the modulus, because the absolute value is a continuous function. So the limits and the absolute value can be changed, can be interchanged. So I have the absolute value within inside, and then I can just break it up. Okay, I will have an absolute value here as well. Sorry. Okay. Then I can just break it out. So I will get limit x tends to x naught, absolute value of fx minus fx naught by x minus x naught, which will give me L, plus x minus x naught and x minus x naught get cancels out because I have limit x tends to x naught and x is not exactly equal to x naught. So I have L there. Right, so this give me L itself, so it subtracts out to get you 0. And what can you do conversely? How can you prove that f is actually differentiable at x naught? Just compute out this limit. So what you have here is that if you again distribute it out, you get fx minus fx naught by x minus x naught minus L is equal to 0. This limit goes to 0. Therefore, this quotient fx minus fx naught by x minus x naught, this converges to L, right? And since x naught is given to be a limit point, you can obviously bound x within some region around x naught, and whenever x is in that region, fx minus fx naught by x minus x naught tends to L. So therefore, by definition of differentiation or by definition of derivative, L must be exactly equal to the derivative at x naught, and f is indeed differentiable. And you can observe that in our proof this is exactly the line we used, right? Now this is something which we will be trying to mimic, okay, because this definition can be actually mimicked. Okay, what is important about this definition to observe? So observation, Fine. That is, this f prime x, this f prime x naught can be interpreted as a scalar, L, such that this limit fx minus fx naught plus L times x minus x naught, this is very small, is small in the sense that it tends to 0 even after dividing it with a very small number. What is that small number? X minus x naught. Dividing it with a small number modulus of x minus x naught. Fine. So the other way of saying is that this implies that fx minus fx naught, this is, as since it is very small, so it is approximately equal to 0, or in other words fx minus fx naught is approximately equal to this, or which implies fx is approximately equal to fx naught plus L times x minus x naught. Therefore at x naught fx is approximately equal to the tangent line. Fine. Clear? Okay. Okay, wait a minute. Yeah, fine. Okay. Clear? And this was something which we said previously, right? That whenever f is differentiable at some point, then it is around that point, it is approximately, it approximates the tangent at that point. So in this way we try to mimic out this definition a bit. Okay. So see, what we try to do is that we keep this in mind, that if I have an arbitrary function f from Rn to Rm, what we try to do, we are intended to linearize f at a point x naught in Rn. Okay, that is how we try to mimic out this definition. Clear? So keeping this in mind, okay, one more thing to observe here is that now when we are in an arbitrary space, this scalar L need not be a scalar anymore, but what we will be making use is of a linear transformation. Okay, and why we require a linear transformation, it will be more clear as we go through these topics. So it will come up in some other lecture, that why do we essentially require a linear transformation, but in fact in the definition itself it will be far more clear that why we require a linear transformation. So let me define the general derivative definition. Let E be a subset of Rn and f from E to Rm be a function, let x naught in E be a limit point of E, and let L from Rn to Rm be a linear transformation. One thing, in the previous example I had omitted the fact that I need x naught to be in E. I actually need x naught to be in E here, where I did it, x naught be a limit point of E. Okay, I need x naught to be inside E, otherwise this limit, the definition of this limit, how we have defined this limit, needs x naught to be in E. Okay. Yeah, so we have x naught in E to be a limit point, and then L from Rn to Rm is a linear transformation. We say f is differentiable at x naught with the derivative L if limit x tends to x naught over x coming from E minus x naught, the norm of fx minus fx naught plus L times x minus x naught divided by the norm of x minus x naught equals 0. Now each of these norms are real valued functions, right? You have studied norms, they are just the generalization of lengths in vector spaces. So these are real valued functions and hence this quotient is now well defined. Okay, clear? And here L is a linear transformation, you need to keep that in mind. L is a linear transformation here. Fine. Okay, clear enough? Okay, yeah. So this is the definition of derivative in an arbitrary case. Okay, so where this norm of x is defined as this, we know, right? So this is the root over of x1 square till xn square, and each of these the norm of the above will be the similar norm in the m dimensional space. Fine, if norm in the m dimensional space. So what we are trying to do here is that here we do not have the slope, the notion of slope in case of a single variable derivative. To be there it was just a scalar, right? Here we cannot talk about a scalar. Here we have multidimensional structures. So here the slope is mimicked by a linear transformation. The approximation in this case is done by a linear transformation. So here we are still holding up the fact that we are trying to linearize f, but here the linearity is approximated using a linear transformation. That is why in the previous lecture we had talked about linear transformation, in order so that we have the notion of how a linear transformation looks like. Okay, clear? Let us quickly start with an example. So let f from R2 to R2 be the map f of xy equals to x square y square. So let x naught be the point 1 2, and let L be the linear transformation from R2 to R2 given by L of xy is equals to 2x 4y. Okay. So what we claim is that f is differentiable at x naught with f prime at x naught equal to L. So this is okay, let me not use this symbol here. Okay, with the derivative being L. Okay, so observe. Okay, so what do we require? We require to use the definition itself. Okay, we require to use this definition itself. Just put in the values and check, nothing else. Okay, so limit xy tends to 1 comma 2 and xy is not exactly equals to 1 comma 2, we want to check out this quotient f of xy minus f of 1 2 plus L of xy minus 1 2 divided by the norm of xy minus 1 2. Okay, now see xy minus 1 2, this can be written as the ordered pair x minus 1 y minus 2, right? So this limit can further be evaluated in this way. Without taking the ordered pair xy to 1 2, we can take the ordered pair ab to 0, where a is just x minus 1 and b is just y minus 2. So I can take this limit to be ab goes to the origin, ab is not exactly equal to this origin, not exactly equal to the origin. And so how does this differ? So this becomes, so x becomes a plus 1, because I am replacing x by so I am replacing x by x minus 1, and that is x minus 1 is being taken to be a. So a is just x plus 1, this is just b plus 2 minus f of 1 2 plus this becomes L at ab divided by norm of ab. Fine. So now just we need to put out these values. So I am not writing the limit again and again. So then this structure becomes, so just put the value. So what is f? F was x square y square, right? So this is just a plus 1 squared, b plus 2 squared, minus f at 1 2 was 1 4 clearly, and L at AB it was 2a 4b divided by the norm of AB. So let it be norm of AB, pay it off now. So this is the norm of, so what does this evaluate to? So if I expand out this a squared b squared parts, so I will get 1 here, 4 here, I will get 1 and 4, they will cancel out, the 2a and 4b will cancel out, so I will be left with a squared b squared by AB. Fine, and all of this is happening when limit AB tends to the origin and AB is not exactly equal to the origin. Right? Yeah. So now what can we do here is that something which you can immediately observe, that now the norm of a square b square, this is equals to the norm of a square times 1 comma 0 plus b square times 0 comma 1. So this is exactly equal to a square plus b square, or sorry, not exactly equal to, less than or equals to, by the triangle inequality, right, by the triangle inequality, because the norm of 1 0 is 1 and the norm of 0 1 is also 1. These are the standard bases, right. Therefore this quotient a square b square upon AB, now this will get evaluated to root over of a square minus b square, and above we have a square plus b square. So the bottom will be evaluated to root over of a square plus b square, above we have a square plus b square. So this is less than equals to root over of a square plus b square, which goes to 0 as AB tends to 0, right. Therefore we are done. Clear? Clear? Fine. Now one more theorem, or rather a lemma, which we can check out here, a lemma, is that its derivative is basically unique. Okay, that is, let E be a subset of Rn, f from E to Rm be a function, let x naught in E be an interior point, for example, is an interior point of E, and let L1 from Rn to Rm and L2 from Rn to Rm be linear transformations if suppose f is differentiable at x naught with derivatives L1 and L2, then L1 must exactly be equal to L2. Okay, this is what we require. Clear? Clear? Fine. You can try the proof on your own. Proof. I am just giving a hint. Suppose L1 is not equals to L2, then this implies that there exists some V in Rn such that L1V is not equals to L2V. Also V is non-zero. Why is V non-zero? Because if V is 0, then L1V must be 0, because L is a linear transformation. Linear transformations evaluated at origin is 0. So L1V not equal to L2V, this immediately implies that this vector V must be a non-zero vector. Then just apply the definition of derivative, and check the case where x is just x naught plus t times v. for some t, and you will come to a contradiction. Okay, you will come to a contradiction, just check it out. Fine. Okay. So what does the definition typically say? The definition typically says that fx minus fx naught minus L at x minus x naught, that must be exactly equals to so that both of the limits must be same, right? Both of these limits tends to 0, these limits are same because f is differentiable at x naught with respect to L1 as well as L2, and the linear transformation evaluated at x minus x naught, it will be exactly be the linear transformation evaluated at t times v. But once we evaluate it at t times v, because it is a linear transformation, the scalar will come out. So, we will get t times L1v, and L1v is not equal to L2v. So, if you evaluate out this limit, you will eventually reach the point that you might get a contradiction at some point using just the definition of linear transformation where the scalar will come out and just applying the definition of derivative. So, try it out. Fine. Okay. Fine. Now, what we actually have here is that this f prime x naught, so here the derivative is exactly f prime x naught, this is the notation, but what to keep in mind is a linear transformation and not just a scalar quantity. It is a linear transformation from Rn to Rm whenever the function we are working with is a map from Rn to Rm. And also in the previous lecture we had seen that to every linear transformation we can associate a matrix, which we can similarly do here as well. We will be able to have a matrix associated to this derivative, which we call the Jacobian matrix. We will do it later, which we call the Jacobian matrix, and this will make computation using derivatives much easier. Okay. Yeah, fine. Moreover, what we can see is that, as I state, that we are keeping in mind the linearization of the function. So, in case of the one dimensional case, we were trying to linearize it with respect to the tangent line, and here we are trying to linearize it with respect to this linear transformation, because the transformation itself is linear in nature. So, what we are having here is that fx minus fx naught is approximately equal to this linear transformation evaluated at x minus x naught. Because the denominator which we are dividing by is also a very small quantity, because x is taken in some very small neighborhood around x naught, and we are taking the norm of that. So, it is also a very small quantity. Okay. The other way of writing it in this way, fx is approximately equal to fx naught, right, and this is what we call the Newton approximation. Okay, this is what we call the Newton approximation. Right. One more thing you can observe, that if I have two equal functions, that is if fx equals to gx for all x in E, and if one of them is differentiable at x naught, then the other must also be differentiable at x naught whenever we are concerned about interior points. Okay, that is something to keep in mind. Okay, so I have this, and if f and g are differentiable at x naught, then their derivatives at every interior point. At every interior point x naught. Okay, this need not be true in boundary points. True at boundary points, because as vectors over boundary points, like there are certain things to talk about, like for example orientable surfaces and non-orientable surfaces. There is a specific direction whenever we talk about the boundary points, that the direction of the vectors might get inverted a bit. Okay, that is some other part to talk about, but this equality need not hold as vectors, because these are linear transformations. So, they being evaluated at some vector is again a vector, right. So, they need not be, so this equality need not hold at boundary points, okay, but they will hold at every interior point. Fine. Okay. So that is what I mean to say is that even if they are equal at the boundary points, still their derivatives need not be equal at the boundary points. Okay, so but whatever we will be dealing with is inside is in the interior point, so we are good to go. Okay, yeah. So that's all for this lecture. In the next lecture, we will talk about how can we define the notion of derivatives in some specific direction, which will be essentially required to talk about the Jacobian matrix. So meet you guys in the next lecture.